Assalamualaikum. My name is Arbaayah Binti Jaafar. We are Group 4 for BEKE 2333 Analogue Electronic PBL assignment. Right now, I'm going to give introduction about our assignment presentation. This is the list of contents for our presentation that will be covered by each of our group mates. They will explain thoroughly for each contents in the upcoming slides. For the introduction and overview of project, we are assigned to question 4. The question 4 also briefly explains about IR communication, and the question requires us to design a Class A power amplifier where the output LED has a continuous power approximately 0.5 watt every time the LED turns on and efficiency more than 6%. The question also gives us a circuit diagram to give us an idea of how we're going to design the Class A power amplifier. Since we are required to design a Class A power amplifier circuit, I'm going to give a briefly introduction about what Class A amplifier is. Class A amplifier conducts through the full 360 of the input. The output of Class A power amplifier conducts for the full 360 of the cycle. As you can see at the picture attached, the Class A full swing 360. And also the Q point is set near the middle of the load line. The Q point is set at the middle of the load line so that the AC signal can swing a full cycle. The DC load line indicates the maximum and minimum limit set by the DC power supply, as also you can see at the picture attached with this slide. There is also written that operating cycle is 360 and also power efficiency is between 25% to 50%. Efficiency also refers to the ratio of output to input power. The lower the amount of conduction of the amplifier, the higher the efficiency. This is the introduction to series fed Class A power amplifier circuit. The difference between this circuit and the small signal circuit is that the signal handled by the large signal circuit are in the range of volts. The transistor used is a power transistor that is capable to operate in range of a few to tens of watts. Further explanation about circuit used in designing this Class A power amplifier will be explained in the upcoming slides. This is the methodology that we use in designing Class A power amplifier circuit as required in the question. First, we understand and observe the question. Second, we make Philaus table to list the requirement for this assignment. Third, we do calculation for type A power amplifier based on parameters given at the question before we designed it. After that, we design the circuit configuration for type A power amplifier using the values of what we have calculated for type A power amplifier. And after that, we construct the circuit and do the simulation using multi-sim live. And then we analyze the result from the simulation. Then we check whether the result fulfill the requirement for the problem or not. If yes, then we proceed to record the data and make conclusion. If no, we then repeat again the step for doing the calculation for type A power amplifier, and the step goes on until we have until we achieve yes for our result checking, and then we can proceed to record the data again and make conclusion, and then after that we finish designing our circuit successfully.
Assalamualaikum warahmatullahi wabarakatuh. Selamat petang. Saya Muhamad Marzuqi bin Mohamad Ruzlan. I will present about the calculation part. Okay, for the calculation we need to set a VCC 12 volt, set beta 25 volt, set efficiency 25%, maximum efficiency. P out kita set 0.5 watt. Okay, step pertama we need to calculate P in. Okay, P in we use efficiency equal to P out per P in. P in equal to 2 watt. For step 2 we need to find RC. Formula is we need to use P in max equal to V kuasa 2 CC per 2 RC. For the RC the value is 36 ohms. Okay, next step we need to calculate ICQ. We use formula P in max equal to VCC darab ICQ. For ICQ equal to 0.167. For the step 4 we need to find RB. Formula untuk cari RB kita perlu cari dulu IB. Cari IB kita guna formula IC sama dengan beta IB. Kita dapat IB sama dengan 6.67 mA. Lepas tu masukkan IB dalam formula VCC, tolak IB RB, tolak VBE, samakan dengan kosong. Lepas tu nilai RB kita 1694.1 ohm.
For the next step of the calculation, we need to determine IC saturation and VCE cutoff. This is for the DC load line X and Y intercept, which determine the maximum output for the power amplifier. IC saturation we get 0.33 ampere and VCE cutoff is equal to VCC, which is 12 volt. Then using KVL we can get VCEQ. This is another thing to determine the Q point. With the calculation we get VCEQ equal to 6 volt. This is the circuit. From the calculation, RB and RC that we obtain, we put at the circuit. This is the DC load line and show how the voltage and current swing. Since the Q point is at the middle, so voltage and current swing can make a full swing 360 degree, full cycle swing. For the voltage, it swing from 0 to 12 volt, and the current, the swing is from 0 to 0.333 amp.
Good morning to everyone. So I'm going to continue for my part, which is stimulations. So this is our AE assignment circuit design. We are using NPN type BJT. So first we need to set up our V sign value, which is voltage peak is 1 volt, frequency is 1 kilohertz, and phase is 0 degree. So next we will put the voltage and current probe at the Q point and current probe at the IB and IE. So we will stimulate this circuit design by using DC operation mode, and then we stimulate, we get the value IB equal to 6.5486 milliamps, IE is 170.26 milliamps, and our Q point is 6.1063 volt and current 163.71 milliamps. Next, we are going to run this circuit design using transient mode. So here we get the output waveform. So we unclick the unnecessary waveform. The purple color waveform is our input voltage, which is from this point to this point we have 1 volt voltage peak, and for one complete cycle we have 2 volt peak to peak. So from here, this one is our voltage waveform and the dotted line is the current waveform. So first we will measure for the voltage waveform. So we'll choose the cursor, choose track, then cursor 1 choose for voltage, move the cursor. So here is the value for our voltage waveform, which is 11.154 volt. If we want in negative form, then we move the cursor forward, then we have the negative value. So next we will measure for the current waveform. Change the cursor to current IC. So this is our current waveform. So we have the current waveform value is 308.32 milliamp. So that's all from me. Thank you.
So my name is Yap Zhi Xuan, and now I'm going to proceed to the next part of our presentation, which is analysis for our mini project. So now we are going to have a look first at the values we obtained from DC analysis and also NC analysis through calculation and also through simulation. So first, the Q point for theoretical. ICQ we get 167 milliampere, while for VCEQ we get 6 volt. For simulation, the value for ICQ we get is 163.71 milliampere, while for VCEQ the value we get is 6.1063 volt. So as we know, our circuit is a class A power amplifier, and our I saturation is 333 ampere, while the VCE cutoff will be 12 volt. So the Q point here will be located at the middle of the DC load line. Next, from the base current and emitter current, as we can see from the table, both the value obtained theoretically and through simulation are approximately the same. For AC analysis, the maximum output voltage swing for theoretical is 12 volt peak to peak, while for simulation is 11.158 volt peak to peak, which is approximately the same and quite close to 12 volt. Lastly, the maximum output current swing for theoretical is 333 milliampere peak to peak, while for simulation is 309.75 milliampere peak to peak. Now we are going to have a look at the output waveform for both theoretical and also simulation, which we obtained during AC analysis. And the output waveform on my left will be the output waveform which we sketched ourselves based on theory, while the waveform on my right is the waveform which we obtained through simulation using multi-sim. Okay, so and on the simulation output waveform, the dark green waveform is the voltage waveform, while the light green waveform is the current waveform. And as we can see here, both output waveform for theoretical and also simulation, both of them has a sinusoidal shape. And as we know, the output of a class A amplifier conducts for a full 360-degree cycle, which is shown by both the output waveform here. Next, we will have a look at the calculation of payout and efficiency based on the simulation result. So as shown by my group member just now, the VCE peak to peak obtained from simulation is 11.158 volt, and the I collector peak to peak is 0.309 ampere. And for power output, we can be calculated using the formula VCE peak to peak times by IC peak to peak divided by 8, and we get a value of 0.431 volt. For P in, we can recalculate through the formula VCC times by ICQ, and we get 1.956 volt. And finally, efficiency, we can be calculated through P out over P in times by 100%, and we get a value of 22.03%. So in general, our circuit has a P out of 0.431 volt and efficiency of 22.03% based on simulation. Now for input and output power, the P in and P out we obtain through calculation theoretically is 2 watt and also 0.15 watt, while for simulation the P in is equals to 1.956 volt and also P out equals to 0.43 volt. For efficiency, since we assume that our power amplifier has a maximum efficiency, so our efficiency for theoretical will be 25%, and the efficiency for simulation as shown just now is equals to 22.03%. Okay, so they are all approximately the same, and the differences may be due to the power losses which we did not consider when we are doing the calculation. So conclusion, now I'm going to conclude our whole mini project by reviewing the 3 main objectives of this mini project and see whether we have successfully achieved all of them. So first, the class A power amplifier design have to generate more power output to LED. So as we know, we have successfully amplified the input current and also voltage to a higher value. So yeah, this first objective has been achieved by us. Next, the output LED has a continuous power approximately at 0.5 watt. So as shown by the previous slide, we calculate the power output based on simulation and we obtain a value of 0.43 watt, which is approximately the same, which is approximately 0.5 watt. So the second objective has also been achieved. And lastly, the efficiency must be more than 6%. Okay, so for our circuit we construct at multi-sim, our efficiency that we managed to calculate is around 22.03%, which is much higher than 6%. So yeah, the last objective has also been achieved. So basically all the objective for this mini project has been successfully achieved. And yeah, thank you.